we do this design, what we're developing here is a sacrificial mold to actually cast the cells in the manner that we want, and we utilize the bioprinter to do so that way, like I say, we have that dissolvable material.
Here, we print like the molds. This is artificial mold, and what we do is put a pillar platform that he will show. This is fake muzzles. We don't have access there.
Sure.
So there's a machine that is right there. When we can analyze, like when we stimulate this muzzle as Mark, we can check this movement and automatically all the wheels at the same time measure this contraction in force, all the parameters like contractility, speeds, everything. All what and here we have actually.
It can't be many micronewtons or whatever in terms of
additive manufacturing, so you do one layer on top of each other, and then you can design like Christina said, and then at the end you also take advantage of nature, right? So it's not trying to reconstitute everything from the beginning.
Right, lab structures to increase surface area for cell culture, and so what we have here is achieve, as Mark describes, replicating the tissues, and you need that kind of fidelity to be able to replicate that. Where the novel hydrogel that we invented, really plays a critical role in that.
Rearrange the labs if you need it. Everything comes from the ceiling. From the construction point of view, it's much more simple.
This lab was purpose built just for this.
purpose arranged.
Purpose arranged from scratch. Purple wall, everything. So,
Can I ask if your director would have...
That would be ideal. And so we have a balance of therapeutic development programs, and then we try to bring these research models in to test the regulatory process and try and improve it. So that's really how we try to integrate the therapeutic development expertise we have. And that expertise is really focused on rare disease, environments where there's, and therapeutic areas where there was really not a lot of commercial mandate to develop therapeutic programs. It's a 10-year timeline. The robots here might have a 3-day involvement in that particular process. It's incredibly impactful. It can screen hundreds of thousands of compounds. We've got assay biology labs across the corridors. So these robots have around them everything that they need to do the experiment. So it's the same equipment that would be in the lab doing this kind of assay dev in a pharma company, a biotech, or an academic drug discovery. Yes, they're better at washing their hands and they never drop the plate. Experiment by experiment, they have to automate that. And what I'll tell you is the robots are live at 2 a.m. If you remember your old days from being in a lab, if the cells are confluent and you need to split them and passage them, it does that for you. If you say I need 4 flasks, when you split it, they'll be ready the next day for you. So, really great way to mainly help us with advanced cell experiments. We wouldn't roll all cell lines, and then they can be delivered. That's a lot of pipetting. So the way we try to show this to people is you can take food dyes, which the FDA approved, but you would not, right? And put them in here, and you can actually teach it to create something. So this is an example of an image that you can.
He planned it in advance.
So